Hello, we're going to start part 2 of the electrical circuits tutorial series discussing Ohm's law and the power formula and also relationships between voltage, current, and resistance. We need to remember that it takes 1 volt to push 1 amp through 1 ohm, and the relationships of our voltage or current or resistance. We know that current is directly proportional to the voltage and inversely proportional to the resistance. So what that means is if we hold our resistance constant and we increase our voltage, we're going to increase our current. If we decrease our voltage, our current is going to decrease. Now, since current and resistance are inversely proportional, if we hold our voltage constant and we increase the resistance, it's going to drive our current down, and if we decrease the resistance, the current's going to go up. The reason these relationships are so important, they can save us a lot of time, save us from having to do the math if you're a technician. They can give us clues as what to look for, where to look for on a circuit that is having a problem. So we'll use a light circuit for example. If our light is actually lighting but it's not bright as it should be, we know that our work, we're not doing as much work as we should be, so our power, our wattage is low. Our voltage and our current, we multiply those, that will give our wattage. So we'll start by making a voltage reading. That is the easiest measurement to make because we use a voltmeter in parallel to a circuit, so we don't have to do anything special to the circuit like turn it off, disconnect something. We don't have to use the lockout tagouts. We simply set it on the right setting on our multimeter, either DC voltage or AC voltage. Once we measure it, and we can measure our voltage drop across the power source, across the individual component, and we see that we have the right amount of voltage, then, and we're not getting the work we should be, then we know that our current has dropped, because our current times our voltage gives us our power. And for that current to drop, if the voltage has remained constant, we know we have an increase in resistance somewhere in that circuit causing the problem. That increase in resistance gives us a clue as what some of the things to look at, some of the places to look in that circuit. A loose connection, corroded terminal, corroded wires, a loose light bulb, a switch or something else in that circuit that has been in use for a long time and has some wear on it and has changed value, increase in the resistance. So by knowing these relationships as a technician, you can save yourself a lot of time and also from having to do the math. Now when we get to Ohm's law and the power formula, we have two basic formulas. Ohm's law would be our voltage is equal to the current times resistance, and our power formula is our power is equal to our current times the voltage. Here's the big thumb wheel. It's a formula chart. It has all 12 of the formulas that we would be using. And as you see, it's kind of intimidating looking. It's got some square roots and some squares, and it's got all 12. So one thing we got to remember, if you're going to use this wheel, you have to be able to reconstruct it every time exactly as it's shown, because if you get one formula out of place, it drives 3 others out, and that would be causing some problems on your calculations. I'm going to use memory aid of ear and pie and show you 4 individual thumb wheels that we can derive all 12 formulas from the 4. The first 2 are the main 2, and those will be the ones I use the memory aid of ear and pie for. As you see, the thumb wheel is a circle that's divided into an upper and lower sphere. That would be a fraction or a division format. The lower sphere is divided in half side by side, and that would be a multiplication format. So E is for voltage, A is for our current, and R is for our resistance. That's our ear. And the way we would use this, if we had our current and our resistance and was looking for the voltage, we'd simply place our thumb over the E, and that would tell us our voltage is equal to your current times the resistance. So now we can derive the other 2, because we can get 3 formulas from each one of these, and we don't have to use any opposites. We don't have to manipulate the algebraic formulas with this due to the design of the thumb wheel. So if we was looking for the A, the amperage, we'd cover up the A, and that would tell us our current is equal to the voltage divided by the resistance. If we was looking for resistance, we'd cover up the R, and it'd tell us our resistance is equal to our voltage divided by the current. And that gives us a fourth of the formulas, 3 of the 12 formulas, and everything. As long as we have 2 values, we can solve for that third one. And we don't have to manipulate the formula any. The thumb wheel does that for us. Now that's ear. Now we'll go on to pi, which is our power formula. And it's set up and used the same way as the ear, but this is using our power, which is our wattage, the amount of work we can do, our current, and our voltage. And so getting into it, to derive the 3 formulas that we get from it, is our power is equal to the current times the voltage. If we're looking for the current, we cover up the I, and that tells us our current is equal to the power divided by the voltage. Looking for our voltage, we cover up the E, and it would tell us our voltage is equal to the power divided by the current. That gives us half of the formulas. That gives us 6 of them from those 2 thumb wheels, and we didn't have to do any manipulation. The thumb wheels did it for us. Now the last 2 are a little bit more difficult. It requires a little bit more manipulation to use, but it'll give us the remaining half of the formulas we can use. Starting off with the one on the left, and we're going to have to use square and square roots to deal with these, but the one on the left, we'll start with it. If the values that we're having and looking for power, current, and resistance, we'd use it. Our power would be equal to current squared divided by, current squared times our resistance. If we're looking for the current, here we got to do a little bit of manipulation because we're looking for the current, not current squared. So we'd cover up that I square, and we'd take current is equal to the square root of our power divided by the resistance. If we're looking for the resistance, we cover up the R, and that would be power, resistance is equal to power divided by current squared. Now for the wheel on the right, dealing with voltage, power, and resistance, we have to do our manipulating from the start. If we're looking for voltage, we'll cover that up, but we're not looking for voltage square. So voltage is equal to the square root of power times resistance. If we're looking for the power, we cover up the P, and it would be equal to, power would be equal to voltage squared divided by the resistance. And if we was looking for resistance, we'd cover up the R, and resistance would be equal to voltage squared divided by the power. Now here's all 4 of the thumb wheels, the individual thumb wheels together. The top 2 again will be the most commonly used as a technician. And with these 4, we can derive all 12 of the formulas from them. Again, the bottom 2 requires a little bit of manipulation. All 3 methods work quite well. Some people, the big 12, the big thumb wheel, is what makes sense to them. That's how their brain's wired. I know people that just memorize all 12 of the formulas, and then a lot of people will use these. It all depends on how your brain is wired, which makes sense and is easiest for you to remember, because they all give you the same formulas. That concludes part 2 of our tutorial. Thank you.